welcome Michael Kesden from now NYU to Nordita here today. He did his PhD together with Mark Kamiakowski at Caltech, has then been spending 3 years postdoc at Tidal, and then went back to Caltech for another 2-year postdoc and has been at NYU since 2011 or 10 maybe, something like that.
Fall 2010.
All right. Okay, so he will be talking to us today about black hole spin and using this as new astrophysical probes. Please.
Thank you for the introduction. So today my talk is going to focus on 2 different astronomical observables that we can use to try to measure the spins of black holes that are out there in the universe. The gravitational waves emitted during the binary merger of black holes, and the tidal disruption of main sequence stars by supermassive black holes. So the talk is going to be in 2 parts about these 2 different phenomena. I'm going to talk a little bit about what black holes mean for relativists, for cosmologists, and astronomers. I'm going to talk about how the gravitational waves emitted during the merger of black holes allows us to probe these black holes directly. I'm going to tell you about the 3 theoretical tools we use to model the gravitational waves from black hole mergers, discoveries I've made using each of these 3 tools, and some future directions in this area. Then in the second half of the talk, I'm going to talk about tidal disruption events, a bit of the history of these things, which is kind of interesting. They kind of fell out of favor, and then there's a lot of interest in them now. I'm going to talk how they've recently been observed in the X-rays, gamma rays, UV, and optical. Some work I've done showing that the rate and the duration of individual tidal disruption events depends on the spin of the black hole. And finally, some future thoughts about work in this direction. So, I'm a theoretical physicist. I look at the universe not as an end in itself, but as a way of learning more about the physics that governs how it works. Most of my thesis work with the Mark Kamiakowski at Caltech was on the cosmic microwave background, and in particular the weak lensing of that background. You guys are probably familiar that large galaxy clusters can shear out galaxies in the background of them, distorting the shape of these galaxies. The same thing happens to the CMB, which is all the way at redshift 1100. Distortion of this pattern of temperature and polarization and isotropies can be used to reconstruct the structure, learn about dark matter and dark energy. I've done other cosmology projects as well. I did a project looking at the tidal disruption of the Sagittarius dwarf galaxy by our own Milky Way galaxy. Stellar debris from this dwarf galaxy gets spun out into leading and trailing tidal streams that have been observed. The relative number of stars in the leading stream versus the trailing stream turns out to be a sensitive probe of dark matter, long-range interactions. I've also done some work on a way to look for primordial black holes using helioseismology, the idea being that a small black hole will pass right through our sun, go out the other end, and cause oscillations in the sun that you can see as oscillations on its surface. These are a bunch of different projects that I've done in the past. I don't really have time to talk about them now. Today I'm going to be talking about black holes. If we want to try to test gravity, gravity is most extreme in the immediate environment of black holes. Black holes mean different things to different people. To relativists, black holes are a vacuum solution to Einstein's equation. They have an event horizon, and they have an ergosphere if they're spinning. Black holes are uniquely described by their mass and their spin. They're some of the simplest objects in the universe. To cosmologists, to people interested in the universe as a whole, supermassive black holes reside at the centers of galaxies. We've been observing quasars now for many years. There's a whole unified theory of how, depending on what direction we're looking at the supermassive black hole, they appear in different ways. But it turns out that black holes have an important influence on how the galaxies that host them evolve. That's another interesting topic. And finally, for astrophysicists, stellar mass black holes are the endpoint of stellar evolution. Very massive stars burn hydrogen to helium, helium to oxygen and carbon, etc., in a nested series of shells. An iron core forms at the center of very massive stars. Ultimately, degeneracy pressure can no longer support this iron core. It collapses into a stellar mass black hole, and then if that black hole accretes from a companion, we can see it. And X-ray binaries are another interesting object for astronomers. So if black holes are where gravity is at its most extreme, black holes themselves are most extreme when they merge. And we normally think about the merger of 2 black holes as a 3-step process. Early on, there's an in-spiral process when the 2 black holes are widely separated. They're orbiting around each other, and they emit gravitational waves that carry away energy and angular momentum from the system. The black holes spiral inwards, and when they get close enough, they merge. The merger process itself is highly nonlinear. The two independent event horizons merge to form a single common horizon. And then at the end, this perturbed black hole produced in this merger rings down into a single black hole. And this final black hole can be again described just by its mass, by its spin, and interestingly by its gravitational recoil. Generally, the gravitational waves emitted in this process will not be emitted spherically symmetrically. So if you have a burst of gravitational radiation carrying linear momentum in one direction, the final black hole will recoil in the opposite direction. And learning about those recoils is also very interesting. So the gravitational waves produced in this three-step merger process can be studied and calculated using three different tools. Let's talk about how they observe them first. So how do we observe these gravitational waves? There's two different techniques. One, you observe them from the ground. Another, you observe them from space. Ground-based detectors, you have LIGO in the United States. There's two facilities, one in Hanford in Washington State, the other in Livingston, Louisiana. There's also some gravitational wave detectors in Europe, GEOs in Germany, Virgos in Italy. COGRO is going to be built in Japan, and a new LIGO facility is being built in India. So these are 5 detectors spread all over the world, and you can use them as a network to look for gravitational waves. These ground-based detectors are sensitive to waves with frequencies in the range 10 Hz to 10 to the 4 Hz, which is waves you'd expect to be emitted by stellar mass black holes. The initial LIGO, which completed its run a couple of years ago, did not see any mergers, but it was only sensitive to neutron star mergers out to 15 megaparsecs. The advanced LIGO that's going to go on next year and ramp up to design sensitivity by 2016 will see out to 300 megaparsecs. So if you increase your radius by a factor of 20, you increase your volume and your event rate by a factor of 8,000. So that increase in 8,000 should be decisive. In the vast majority of models, we predict that advanced LIGO will see at least several, if not tens, of mergers per year. And finally, ELISA, the European LISA, Laser Interferometer Space Antenna, or Next Gravitational Wave Observatory, is not going to be built for a while. It's being considered for the second L-class mission by ESA, but it probably won't be operational until 2030 at the earliest. And this would see gravitational waves from supermassive black holes that live out to galactic centers, and also the waves produced when small objects fall into the supermassive black holes. The tools we use to calculate these gravitational waves, I like to call the strategic tripod of general relativity. I'm an American, I have to have a military analogy in every talk. But there's 3 different tools. In the strategic tripod in the military, you had bombers, you had nuclear submarines, and you had intercontinental missiles. And we have 3 different tools. We have the post-Newtonian approximation, we have black hole perturbation theory, and we have numerical relativity. So this is the kind of oldest and most venerable tool. It's an expansion when the relative motion, when the potential is not too deep, and the relative motion of the 2 black holes is small compared to the speed of light. And the post-Newtonian approximation is ideal for studying the gravitational wave produced when the 2 black holes are widely separated early in that first stage of the in-spiral. Black hole perturbation theory is probably the least well-known of these tools. It's kind of our stealth weapon. And there we're perturbing not in the speed compared to the speed of light, but into metric perturbations around a background Kerr solution. So this is ideal, number 1, when a very small object falls into a supermassive black hole, you can treat that small object as a perturbation. Or even for comparable mass mergers, at late times, at the very end of that merger, it's ringing down. And so you can also consider those perturbations in black hole theory. Perturbation theory. And finally, numerical relativity, which has undergone a revolution, really. We've only merged the first black holes in fully nonlinear numerical relativity back in 2005. It's a brute force, well, you're solving the nonlinear 10 coupled Einstein's equations directly. It's very computationally intensive, but it's the only way to calculate the gravitational waves emitted in that merger process. I've done projects with all 3 of these tools. First, we'll talk about the post-Newtonian approximation. So generally imagine you've got 2 black holes, each of which are spinning, and the system itself has an orbital angular momentum. And generically you imagine all 3 of these vectors are pointing in different directions, and they'll all recess about each other in some horrible fashion. And that is people's conventional assumption. But in reality, it turns out that Jeremy Schnittman discovered back in 2004 that there are these special attractor solutions where all 3 of the spins align in a common plane, and the common plane precesses together at the same rate. There's 2 families of attractors within this solution. if theta 1 is less than theta 2, if the angle between the spin of the more massive hole and the orbital angular momentum is smaller than the angle between the spin of the less massive black hole and the angular momentum, that's below the diagonal in this plot, the two spins all line up on the same side as the orbital angular momentum. The spins align with each other. Whereas in the opposite case, the spins anti-align with each other. We see here in this plot as some widely separated black holes in spiral to a separation of 1,000 gravitational radii, 100 gravitational radii, and 10 gravitational radii, that if the angle between the two is isotropic, the blue, green, and red points correspond to initial distributions where the angle theta 1 between the spin of black hole 1 and the orbital angular momentum is the smallest third, the intermediate third, and the largest third. These points we can see segregate. It's hard to see, I guess, in this plot here, but the blue points are clustered here near delta phi equals 0, theta 1, 2 equals 0. Those points align with each other. The red points tend to get segregated over here. Separation of 180 degrees, they anti-align with each other. And so this alignment during this post-Newtonian first stage of the in-spiral has important astrophysical consequences, both for supermassive black holes and for stellar mass black holes. So one of the very exciting discoveries of numerical relativity is that rather than just coming to rest when the two black holes merge, as I said earlier, there's a gravitational recoil. The black hole is ejected with respect to the center of mass of the initial binary. And that ejection speed can be as large as almost 5,000 kilometers per second, which is small compared to the speed of light, but compared to any astrophysical velocity, the escape velocity of even the largest cluster, 5,000 kilometers per second is huge. So what we expect to happen is that if we have a pair of binding black holes at the center of a circumbinary disk at a galactic center and they suddenly merge, if they get a large recoil like this final black hole will be ejected from its galaxy. It'll take some gas with it. And so this has kind of started off a search to look for displaced quasars with respect to their host galaxies. And what we've shown is that when theta 1 is small, when the more massive black hole is closely aligned with the orbital angular momentum, which is what you'd expect if it's being fed from its circumbinary accretion disk, then when the black hole spins are aligned in that particular configuration, the kicks are suppressed. Instead of these long distributions with tails out to 3,000 kilometers per second, these histograms show that you pile up at smaller kicks. So this can help reconcile the picture of how all galaxies have supermassive black holes at their center. If post-Newtonian alignment suppresses the kicks and allows galaxies to hold on to their supermassive black holes. It has important implications for stellar mass black holes as well, which are one of the primary targets for LIGO and Virgo and these ground-based detectors. Stellar mass binaries form through the evolution of very large massive stars. Here's an example. Cygnus X1 is one of the first stellar mass black holes that's been observed. We see it accreting from a companion, HDE 26868, which is a blue supergiant. This is a 30 solar mass black hole that may itself collapse into a second black hole at a later time. When these two black holes in spiral and merge, depending on certain factors in their binary evolution, whether or not tides are efficient at aligning the spins of the black hole with each other, whether or not mass transfer between the two holes, which is what you see going on here, can reverse the mass ratio of the stars from their original ratio. This alignment will align the spins either cluster around 0, it'll align the spins with each other, it will anti-align with each other, or you'll get a mild peaks at spin angles of 90 degrees between the two spins. And so this is potentially detectable by LIGO. So this is a nice, interesting way that LIGO will not only teach us about general relativity and gravitational waves, it will tell us about these precursor systems to binary black holes. Here's a project I did involving black hole perturbation theory, that second tool in our toolkit. Black hole perturbation theory, like I said, works either for the ring down at the late stages of the merger, or when a small object falls into a supermassive black hole. We think that supermassive black holes live in galactic centers, and things like white dwarfs, neutron stars can get scattered onto orbits where they in-spiral into these black holes through the influence of gravitational radiation. In theory, black holes can spin all the way up to a maximum spin of 1, beyond which they have a naked event horizon. Bardeen showed in 1970 that a non-spinning black hole, after it increases its mass by a factor of the square root of 6, when it's accreting in its equatorial plane, will spin up to a maximal spin. Kip Thorne back in 1974 showed that in practice, when you're, for gas to get down to that innermost stable circular orbit, it has to lose energy to fall down into that potential well. It has to radiate. And the black hole will preferentially absorb photons that have negative angular momentum. So instead of getting all the way up to a maximum spin, at a spin value of 0.998, there'll be a balance between the angular momentum that the black holes gain when the gas falls in versus the angular momentum that they lose when the photons with negative angular momentum get absorbed. I showed using black hole perturbation theory that there's a very similar limit when you build the black holes not from gaseous accretion, but from these emeries, these extreme mass ratio inspirals. It turns out that at the same value of the spin, but for very different reasons, the angular momentum the black holes gain when these small objects inspiral and fall in is canceled out by the angular momentum energy extracted superradiantly by gravitational radiation. Inwards gravitational radiation scatters off the spinning black hole and carries angular momentum out to infinity. And that balances that gain at a spin of 0.998. So rather than, if we think of a spin of a black hole gaining mass, rather than spinning all the way up to a maximal spin, now due to this calculation perturbation theory, we show they only spin up to a value of about 0.998. This seems like a small difference, but in practice it's a very big one because the spin is not a kind of linear, observables are not linear functions of the spin. For example, the amount of energy lost at the ISCO is 30% for 0.998 and about 40% for a maximally spinning black hole. So this is a big difference, not a small one. Finally, an example of a project I've done with numerical relativity is using symmetry to constrain these very expensive, very finite set of simulations that we have. It turns out that we said black holes are very simple. The initial binary is described only by the mass ratio of the two holes and the spins of the two holes. And the final black hole is determined by its mass, its spin, and its gravitational recoil. It turns out that all of these final quantities vary in well-defined ways under a bunch of symmetries. Parity, that you reflect the system in a mirror. Exchange, you just change the labels of black hole 1 and black hole 2. Things are either odd or even under these operations. And the same is true for those initial observables, the mass ratio and the components of the spin. And so it turns out that that final observables can only depend on initial observables with those same behavior under parity and exchange. And this allowed us to predict, at a time when there was only just a handful of numerical relativity simulations, how quantities like the final kick, the final radiated angular momentum, the final spin, the energy radiated, depended on the orientations of those initial spins. And not only did we explain existing behavior, but we predicted new behavior that was subsequently found in numerical simulations. This kind of very simple approach is surprisingly effective. In many ways, you can think of it as a scattering process, even though these are astrophysical objects. Future directions for work on binary black holes. Number one, I have a background in cosmology, as I said before. I'm interested in how we can connect astrophysics and the universe with relativity, which governs these final late stages. So the way that we do that is we look at the mass ratios and the spins that we expect astrophysics to give us for that early in-spiral stage. I've been thinking about how, when you have supermassive black holes accreting from a circumbinary disk, what mass ratios to expect, what kinds of spin alignments to expect, and how this depends on the host galaxy and how those black holes are accreting. For stellar mass black holes, LIGO and Virgo are going to hopefully start seeing things in 2014, 2015. And we need to construct gravitational wave templates that are accurate to 1/10 of a radian, so we can dig out those gravitational wave signals underneath the noisy background. And understanding the right templates to use to search for the systems depends on understanding what kind of systems astrophysics is going to provide. I think these spin orbit resonances are going to be very important to that story. It hasn't been worked out so far. Generally, one would think that by aligning everything in these common planes, the system would look kind of like a non-spinning system. You wouldn't get that horrible degenerate precession that people had feared. It's a good thing for gravitational wave detection because a limited set of templates, of these non-precessing templates, can be used to search for the systems that we're looking for. It's bad for parameter estimation because the cleaner the signal, the more degenerate all the various parameters in the system are. But this is really uncharted territory. More work needs to be done to understand these effects. Now I'm going to get to the second half of the talk, which happens to do with tidal disruption events. We have a supermassive black hole here at the center. A star comes in. It's ripped apart when the tidal forces of the black hole exceed the star's self-gravity, some of the debris escapes to infinity, the rest of it falls down, forms an accretion disk, becomes luminous, and possibly launch a jet as well. This is what we mean by a tidal disruption event. Supermassive black holes at galactic centers, tidally disrupting main sequence stars that wind up on orbits with pericenters too close to the supermassive black hole. The history of tidal disruption events is kind of interesting. People started observing, powerful radio sources back in the early 60s, and people didn't know what to make of this. They were very bright, they varied on very short time scales. Some people thought it was just a collection of supernovae kind of going off simultaneously because they had no experience of how something could be that bright for that sustained period of time. But that seemed kind of funny to imagine all these supernovae at galactic centers happening simultaneously. So instead, Fred Hoyle and Willie Fowler back in '63 argued that rather than being supernovae, these kind of bright radio sources were instead very massive, compact, stellar type objects. They thought this was a very strange idea, but very nature of the case demands an unusual physical situation. But to the argument that a giant 10 to the 8 solar mass star would be unstable, we turn a blind eye. They ignored that possibility. But other people couldn't ignore it. The thought was that something that massive would collapse very quickly to a supermassive black hole, and a black hole is black. Naively, you wouldn't expect to see such things. Lyndon Bell argued otherwise in a Nature paper in 1969. Nothing can pass outside the Schwarzschild sphere radius 2gm over c squared. We call this the Schwarzschild throat. We would be wrong to conclude that such massive objects are unobservable. It is my thesis we've been observing them indirectly for many years. So in practice, even though you're not seeing anything coming out of the event horizon, you're seeing the accretion disk, you're seeing jets. People, even by 1969, had been observing supermassive black holes for a long time. They just hadn't realized it. Once you accept the idea that we have supermassive black holes at galactic centers, then that begs the question, how did they grow to be the size that they are today? Supermassive black holes, originally people thought they grew by tidal disruption. People thought that if you have stars and galaxies, stars would wander to galactic centers, they'd get ripped apart, and you'd accrete that way. So this was tidal disruption events were originally a subject of theoretical interest as the way to grow supermassive black holes. However, subsequent work showed you just can't feed stars into galactic centers at the rates necessary to grow black holes up to those big masses in such a short amount of time. We see black holes out to high redshifts, and they have very large masses comparable to those they have today. So instead, currently, the prevailing idea of how supermassive black holes grow is partly by merging with each other, but primarily by just, rather than accreting tidally disrupted stars, accreting from gas, which is driven to galactic centers during major mergers. Unlike stars, which are collisionless, and you have to wait for slow scattering processes to refill these orbits that get close to a black hole, gas can cool, and so gas can very rapidly refill orbits that would allow it to get sucked into the black hole. So black holes grow primarily through gas accretion. Simulations by Barnes and Hernquist showed that in 1991. So around this time, people lost interest a little bit in tidal disruption events. However, Martin Rees generated interest in a Nature paper from 1988, a new idea that maybe black holes don't grow primarily through tidal disruption events, but if a star does wander too close to a supermassive black hole, the star gets ripped apart, roughly half of its mass will go on bound orbits, get subsequently accreted, so a dark, quiescent black hole sitting there by itself could all of a sudden, in very short timescales of like a month or so, brighten up into a maximally accreting black hole. And so looking for these bright transients could be something of interest to astronomers. And once this idea came out, the tidal disruptions, rather than being an ugly, kind of failed idea for supermassive black hole growth, became some beautiful exotic object that observers would look for. And so look for it they did. People looked for it starting in the X-rays. Rosat was a German X-ray satellite that did an all-sky survey. And during the course of that survey, they found 5 supermassive black holes where at the beginning of the survey there was no X-ray emission, consistent with 0. And then over the course of that 5 years, which is brief on astronomical times, the X-ray luminosity increased by greater than a factor of 80, increase in X-ray luminosity. So these were TDE candidates. XMM Newton is a later X-ray telescope, which also did another all-sky survey, and they looked at galaxies that were quiet during Rosat, but then had a brightening by several years later when Newton did its survey. Here are an example of 5 such systems that they found. They found another 5 proposed tidal disruption candidates in the X-ray. More recently, TDE candidates have been seen in the UV. GALEX is the Galaxy Evolution Explorer. It's a UV satellite that was launched, I think, in 2004, maybe? Early last decade. And so here we see in the far UV and the near UV channels observed by GALEX, looking at a particular galaxy in 2003, 2004, 2005, and 2006. There's no emission in 2003. A bright transient appears in 2004, and it's fading by 2005 and 2006. Only upper bounds in 2003, 2004. A bright transient appears, and it decays. And this decay is consistent with it being a tidal disruption event. It was observed both in the UV with GALEX and in the optical by the Canada, France, Hawaii telescope in their legacy survey, and PanSTARRS, which is another optical transient survey. TDEs have also been observed in the gamma rays. This is another very exciting thing that happened back in 2011. The SWIFT satellite is designed primarily to look for gamma ray bursts. You have a burst alert telescope that has a very wide field of view in the soft gamma rays. They see a transient appear, and then there's a better sensitivity but smaller field of view X-ray telescope. The telescope swiftly swivels and points at the new transients they see. So in March of 2011, the burst alert telescope, all of a sudden the account rates got above their threshold for triggering at t=0 here. They swiveled the X-ray telescope to that thing, and they saw emission that continued and still continues since then, almost 2 years. Typical gamma ray burst, you have short duration bursts that last for about 1/10 of a second. You have long duration bursts that last 10 seconds, but no GRB has been long enough to last for 2 years. So this was a unique object that had never been seen before. There was a lot of interest. Is it some kind of very strange gamma ray burst that just doesn't quit? Is it a blazar that just turns on? Blazars are AGN whose jets are pointed right at us. And we see many of these things, but these things evolve on 100 million year time scale. So 2 years may be short, maybe very long for a gamma ray burst. It's very short for a blazar. It didn't fit into any of these pre-existing categories. So instead, people came to the conclusion that this is most likely a tidal disruption event. And after finding one of them in March, they found a second one later that year that had very many similar properties. And you can look for them in the optical as well. The Sloan Digital Sky Survey surveyed a big portion of the sky, and they did both spectroscopy, and then they had 5 photometric bands. And it turns out by looking at transient events in the Stripe 82, which was a field that was observed with very high cadence compared to most of the survey, and carefully throwing out all your AGN and throwing out all your supernovae and placing rigorous cuts, they found 2 candidate events. This is a before picture, this is an after picture. If you difference the two, you see that there's a bright transient left over at its center. So in all of this Stripe 82 of Sloan, they found 2 candidate tidal disruption events. Now, if you extrapolate based on how much sky coverage Sloan had, how deep it observed, how faint objects it could see, and what cadence it observed, how many times it looked at the field, and compared the predictions of Sloan, which is ongoing, to those that will be done by the Large Synoptic Survey Telescope, which was the #1 ground-based priority of the 2010 National Academy of Sciences Decadal Survey. It's expected to turn on about 2020 or so. This will survey essentially, all the sky you can see from the southern hemisphere. It'll look at the sky every 3 nights, which is a much higher cadence than Sloan, and it'll go deeper than Sloan. It's a bigger mirror, it can collect more photons. So if you extrapolate, and you found 2 with Sloan, you should be able to see thousands of these tidal disruption events with LSST. So given that, in 2020, which is, I guess 7 years from now, we're going to have such a rich sample available to us, we want to think about what science can we extract from that sample, and in particular, I'm interested in can we learn about supermassive black hole spins. So what are the predictions, first of all, before we're physicists, we want to make predictions first and gather our data to test those predictions later on. And the predictions are really all over the map. Here we see, this is a work by Emanuela Berti and Marta Voluntari from 2008. We're looking at, these are histograms, the number is on the y-axis, spin magnitude is on the x-axis, 0 is a non-spinning black hole, 1 is a maximally spinning black hole. Each of these rows corresponds to different redshift bins. Redshift less than 1, the local universe, 1 to 2, 2 to 2.5, 2.5 to 3. The different columns correspond to different assumptions about that efficiency with which spins are aligned with their orbital angular momentum I talked about earlier. You assume that the spins are isotropically oriented with respect to the orbital angular momentum. A line that the smaller black hole lies in the equatorial plane of the larger black hole. And equatorial means that the spins are all lined up with each other. All three, orbital angular momentum and both spins, are all aligned. And you can consider the spins that form just by mergers only. If black holes, galaxies grow, small galaxies merge with each other, form into larger galaxies. Black holes grow in the same way. Small black holes merge, make bigger black holes. If mergers are the only way black holes can grow, you get these distribution of spins. If they can grow through disk accretion, nice coherent accretion in an accretion disk in the equatorial of the plane of the black hole, Shakura-Sunyaev disks that people have been studying for years, these are the spins you get. And if they grow through chaotic accretion, the idea that the real universe is a lot messier than a nice thin accretion disk. You have star formation, you have turbulence, chunks of gas could get accreted by the black holes with random orientations, what they call chaotic accretion. And you see that essentially these three scenarios, reality is probably a superposition of these things, bracket everything from zero, virtually non-spinning black holes, all the way to virtually maximally spinning black holes. So theory gives us not a lot of guidance in the spins to expect for supermassive black holes, which makes it even more interesting to kind of go out and measure them and distinguish between these different scenarios. So how do we observe black hole spins? There have been estimates of supermassive black hole spins. One of the most popular techniques is through iron K-alpha lines. If you have a hot corona around a supermassive black hole, X-rays emitted by that corona will be reflected by the accretion disk. And in particular, a particular line of iron, and the iron K-alpha line, will fluoresce. And the breadth of that line will depend on how quickly the gas is moving around the black hole, which in turn depends on the black hole spin. This solid black curve is for a non-spinning black hole. As you increase the spin to 0.25, 0.5, 0.75, and 0.998, that Kip-Thorne limit we talked about before, the line gets broadened and the distribution extends to lower energies. This idea was kind of introduced in 2006, and once the idea was introduced, XMM Newton, which was one of those X-ray satellites we talked about before that had seen these TDEs, and Suzaku, which is another X-ray satellite, went out and measured the shape of these iron K-alpha lines for 8 nearby active galactic nuclei, listed here, and they found a whole range of spins. Some of them were consistent with maximally spinning black holes. Others had more modest spins. And so this is a small sample that we can use there's certain systematic errors associated with this technique, but this is kind of the first tip of the iceberg in trying to understand the demographics of supermassive black hole spin. So you can do it with iron K-alpha lines. Ultimately, we'll be able to do it with LISA. That's not happening for a long time, unfortunately. But tidal disruption events gives us yet another technique to get at supermassive black hole spins. Why would we want a new technique? Number one, the systematics of reconstructing the spin from tidal disruption events are different from those of these iron K-alpha lines. You're looking at different populations of black holes. By definition, you can only see these iron K-alpha lines if you have an accretion disk. If a black hole has an accretion disk, that accretion will change its spin. Accreting black holes are not necessarily representative of the black hole distribution as a whole, as we saw in Emanuela and Marta Volonteri's paper before. Merging black holes also will not, the kind of black holes seen by LISA also may not be representative of black holes in the universe as a whole. Whereas these tidal disruption events, as long as you have a black hole sitting there at a galactic center, sooner or later stars are going to get scattered onto orbits that get tidally disrupted. So that's kind of an unbiased probe of what all the supermassive black holes in the universe are doing. And also you're probing different aspects of the Kerr geometry compared to this iron K-alpha line, which is just in the equatorial plane. Generally, tidal disruption events will be happening at all orientations. So there's interest in trying to constrain black hole spins with tidal disruption events. How do we do it? I've written 2 papers recently about how the rates at which we see these tidal disruption events and the light curves for individual events can be used to constrain black hole spin. So first, I'm going to tell you a little bit about the Newtonian ideas and then how I generalize those approaches to include relativistic effects, including spin. So if a star gets too close to a black hole, 2 things can happen. Number one, if the black hole's tidal forces, the difference in the force exerted on the two sides of the star, exceed the star's own self-gravity, it can get ripped apart. And by equating those two, the Newtonian tidal force of the black hole to the star's self-gravity, you can find that stars get within the tidal radius of the black hole, they're disrupted. The other thing that can happen to a star is direct capture. If you're really going right in and you cross the event horizon, your star will just be swallowed right by the black hole, and you won't create an accretion disk, you won't launch any jets, the star will go right into the horizon and you'll see nothing. That's what I'm calling direct capture. And that happens when your pericenter is less than the Schwarzschild radius. If you notice, this scales as the 1/3 power of the mass of the supermassive black hole. This scales linearly in the mass of the black hole. So if you go to black holes of larger and larger masses, ultimately this will be a bigger number than this is. And so you'll only directionally capture stars and you won't observe tidal disruption events. And that happens, the Newtonian calculation equating to these two things and solving for m happens at a mass of about 10 to the 8 solar masses, which is interesting for astrophysics. That's very comparable to typical AGN masses that we see. But this calculation was done by equating a Newtonian tidal force to the Schwarzschild radius, which seems like a very dubious thing to do from a relativistic standpoint. So I thought we could do better. And so we generalized this calculation to real relativity. And so what did we do? Instead of considering stars on parabolic Newtonian orbits, we considered stars on real geodesics of the Kerr black hole, characterized by an energy and a z component of the orbital angular momentum and a Carter constant. And so we considered stars on real geodesics, and furthermore, rather than considering this Newtonian tidal force, we used the geodesic deviation equation to see two nearby geodesics, the two different sides of the star, will naturally in relativity want to move apart from each other. The geodesic deviation equation tells you how to do that. If we compare that to the star's self-gravity, we can generalize this equation to a new relativistic tidal disruption radius, which depends on the magnitude of the negative eigenvalue of this relativistic tidal tensor. In the limit that the orbit is far from the black hole, this goes to 2m over r cubed, and you reduce to your nice Newtonian tidal radius. But in general, for pericenters close to the supermassive black hole, this beta minus will depend on the black hole's spin, the orientation of the orbit, and a whole host of things that you can use to characterize whether or not a star is tidally disrupted. So once we've made these relativistic generalizations, we could then make relativistic predictions for the tidal disruption rate. This black dash curve here shows, as a function of the function of the mass of the host galaxy's supermassive black hole, from 10 to the 6 solar masses, which is a small supermassive black hole. Our own galaxy has a black hole of about 4 times 10 to the 6 solar masses, all the way up to 1 million solar masses, which is a very large supermassive black hole. We see that, and this is the rate per year per galaxy of tidal disruption events we'd expect. This black dash curve is a purely Newtonian prediction, which was done by studying the rates at which stars are scattered onto orbits that disrupt far from the hole. These colored curves show now that we include the possibility that these black holes can get swallowed by the event horizon. In the Newtonian predictions, people don't normally consider the event horizon. We see that at small masses, the horizons are really small and essentially insignificant. But as we increase to larger masses, the probability of getting swallowed directly gets larger and larger. The rate of observed tidal disruption events gets smaller and smaller. And so the idea would be, if LSST, the Large Synoptic Survey Telescope, observes thousands of TDEs starting next decade, we can look at the host galaxies of these TDEs. Based on the properties of the host galaxy, we can infer the mass of the black hole. And then if we bin those by mass, and we have an idea for what the mass of the black hole is, and we measure the observed rate, we can try to infer the spin of the mean spin of that distribution of black holes. And so right now we only have that handful of tidal disruption events. It's not a large enough sample to try to do this productively, but very soon we're going to have a lot more. So this is one way we can get at the spins of supermassive black holes. Another way is, but we wonder with our limited sample we have today, with the individual events we see today, do those also depend on the supermassive black hole spin? And yes, they do. The idea behind this approach is that the light curve of a tidal disruption event, the luminosity of the event as a function of time, depends on dm dt, the mass at which the debris of the star is being accreted by the black hole. So what does this mass accretion rate depend on? Just by the chain rule, dm dt is dm de, de da, da dt. Da is the semi-major axis of the debris orbit. So the relationship between the semi-major axis of an orbit and its period is Kepler's third law that we know. This implies dA dt goes as t to the minus 1/3. The relationship between the binding energy of an orbit and its semi-major axis, this we also know. So dE dA goes as t to the minus 5/3. So it turns out that the light curve of a TDE goes as t to the minus 5/3 times the distribution dmdE. That's the mass of this tidal debris, the mass of this disrupted star, in orbits with in a given range of binding energy E. So what is dmdE? That's the question. Martin Rees, when he wrote his Nature letter back in 1988, just assumed dmdE is constant. If you have some unknown function, assuming it's constant is the first obvious thing to do. And so he then got a light curve that would fall as t to the minus 5/3. A more sophisticated approach considers that if this star, when it gets close enough to the supermassive black hole, the star is going to be extended. It's not a real point mass. Some parts of the star lie deeper in the potential well. Other parts in the star are further up in the potential well. These parts that are further up in the potential well will be unbound during the tidal disruption event, and they'll be ejected at large velocities. Parts of the black hole more deeply bound to, deeper in the potential well will become bound. The deeper you are in the potential well when the star is ripped apart, the more tightly bound you are, the shorter the period of your orbit, the sooner that debris will fall back to the black hole and get accreted, and that will power the early portions of the light curve. So essentially the density profile of the star, how much mass you have at a given depth in the potential well, determines the distribution of orbital binding energies and the accretion rate onto the black hole. These three different curves, here this is a dmdE is on the y-axis, the amount of mass with a given binding energy as a function of that energy. These three different curves correspond. The black one is an equation of state of pressure in the star goes as density to the 5/3. The blue dashed curve is pressure goes as density to the 1.4, and this red dotted curve is density goes to the 4/3. So the stiffer your equation of state, the more pressure you have, the more gas you'll have at larger radii in the star, the more gas you'll have deeper in the potential well, the more gas will return to the black hole sooner, and the brighter your curve will be originally. And so for these assumptions about dmdE, this second plot here shows time on the x-axis, dmdt on the y-axis. The stiffer equation of state, pressure goes as density to the 5/3, you have more debris deeper in the potential well, that debris returns sooner, you have a brighter event, and you have it sooner after the disruption occurs. So this is a purely Newtonian calculation that was done by Giuseppe Lodato and collaborators in 2009. But again, I wanted to generalize that to relativity and see how it depended on black hole spin. And so people took this model, they compared it to data. As we said, GALAX, which is this UV satellite, PAN-STARRS, which is this ground-based optical transient survey, has been seeing tidal disruption events for the past few years. PS1-10J is a particular tidal disruption event they discovered back in 2010. It was published in a Nature paper by Suvi Ghazari and collaborators in 2012. Here we see NUV is the near UV. That's ultraviolet observations by GALAX, the points of the observations. G, R, I, and Z are 4 different optical bands done by PAN-STARRS. Green light, red light. These are longer wavelengths. I is kind of like infrared. I don't know why they call Z, Z, but that's the longest wavelength optical light. And we see that if you compare the points, which are the data, to fits based on these purely Newtonian models by Giuseppe Lodato and collaborators, you see it's a reasonable fit. It's not perfect. There's discrepancies at early times. The discrepancy is at late time. But the model isn't completely wrong. And furthermore, if you consider what parameters of the model fit to this data, you find that the star is on an orbit that is a pericenter that's only 6 times the Schwarzschild radius of the black hole. And so you might imagine that Newtonian equations won't do such a good job at 6 Schwarzschild radii. So we want to do better with relativity. So as before, I took a Newtonian model and generalized it to include relativistic effects. Instead of dmdE, in the previous slide we talked about how, according to Kepler's law, the period of an orbit, of a Newtonian orbit, depends only on its energy. That's not true in relativity. In relativity, the radial period of your orbit depends not just on your energy, but the z component of angular momentum, and this quantity q, which is the Carter constant, which is a relativistic constant. The analog is kind of the square of the components of the angular momentum perpendicular to the spin. So instead of a dmdE, we need to calculate a full 3-dimensional distribution, d cubed m, dE, dLz, d cubed. And furthermore, rather than saying the distribution in energy is just the gradient of the Newtonian potential across the size of your star. R minus RP is the kind of width of your star. Now we need relativistic generalizations to that in a slice of space-time perpendicular to the velocity of the star. We can calculate in Fermi normal coordinates over the density distribution of the star, the distribution in energy, and there's an analogous expression for z component of the angular momentum and the Carter constant. It will depend on the metric. It'll depend on E and EI. These are your tetrad of 4 vectors along the geodesic. Xi is the position of a particular fluid element of the star, and gamma is just the connection coefficient that can also be calculated from the metric. So now we have a distribution that depends on black hole spin, and it depends on the energy, angular momentum, and Carter constant of the orbit of this star. And when we make these relativistic generalizations, we see that the dm dt, the rate at which this tidal debris is falling back to the supermassive black hole, does depend on spin and mass, etc. This black solid curve is the purely Newtonian prediction for a black hole of mass 10 to the 8 solar masses. We consider an orbit that has a pericenter of 6m in Boyer-Lindquist coordinates. And we consider here equatorial orbits. The solid red curve is a non-spinning black hole. The orange dashed curves are a black hole with a spin of 0.5. The larger curve is a retrograde orbit, that the orbital angular momentum is anti-aligned with the black hole spin. The smaller orange curve is a prograde orbit. The orbital angular momentum is parallel to the black hole spin. The blue is a spin of 0.99, again, retrograde and prograde. And what we see, this is a log plot. This is a log-log plot. There can be like a factor of 2 difference in the peak luminosity, the peak accretion rate, depending on the orbit of your star for a black hole of this mass. But as we said before, and now, so this is for a black hole of 10 to the 8 solar masses. Now we consider the same thing for a smaller black hole of 10 to the 6 solar masses. Again, the black curve is the prediction. This is, again, equatorial orbits. Red is non-spinning. Orange is 0.5. Green now, the green dot dash curves are 0.9, and the blue is 0.99. So what happens is that when you have a smaller black hole, there's all the scales, the Schwarzschild radius scales linearly in m. The gradients are sharper. You can lose more energy. And one of the interesting phenomena is that if your pericenter is too close, you lose so much energy in the tidal disruption process that rather than falling back and forming an accretion disk or powering jets, you get directly captured. You fall right down the event horizon. And that's what we see for these green and blue curves. Rather than for the retrograde case, rising to large peaks, in the previous plot we saw this blue curve went all the way up to this large peak here. Now, instead of going all the way up here, it falls off really quickly. So you lose the whole early portion of the in-spiral, because all this gas that would have gone on to form an accretion disk has just fallen right down the event horizon before it had a chance to radiate. And so we see it, observing something like this, seeing a kind of a very sharp cutoff in the early light curve of a TDE would really be a smoking gun signature that you've directly seen kind of an event horizon in this tidal disruption events. It would be really exciting to see such a thing. And that can be done in this model. And finally, the stars are scattered onto these orbits very far from the black hole. That generally, at the center of galaxies, the black holes live at the center of these nuclear star clusters, dense clusters of between 10 to the 5 and 10 to the 7 solar masses of stars. Some kind of collisional process at the size of these nuclear star clusters, about a parsec or so, will scatter a star onto an orbit which will have a pericenter close enough to the black hole it will get disrupted. But the process is going on at these parsec scales, at such a larger scale than the Schwarzschild radius, it will know nothing about the black hole spin. And so you'd expect the stars to be coming in isotropically, so you need to be able to handle non-equatorial orbits. And my model can do that, and furthermore you see that the light curves do depend on the inclination of the orbit and the orientation of the orbit. Here I is the inclination, it's the angle between the orbital angular momentum of the star and the spin of the black hole. Theta is an angle that corresponds to, if you fix this orbital angular momentum and then rotate in that orbital plane, that angle also will affect the geodesic, and it'll affect the light curves of your TDEs. And this is showing as we go from a purely prograde orbit to a retrograde orbit, you get higher peak accretion rates that happen sooner. And if you fix the inclination and you rotate it, there's some mild dependence on that angle as well in the observed light curve of these events. So, future directions for work on tidal disruption events. Number one, does the light curve really track this fallback accretion rate? We're talking about, you start off with a star, it's ripped apart, it forms these lengthy tidal streams. But then we assume on some very short time scale, these streams can just quickly turn into an accretion disk, which you hope to see. In practice, that process is not instantaneous, and that process itself will depend on the black hole's spin. I think it will actually depend very sensitively on the spin. I don't have time to talk about that now, but that's another project I want to pursue. Studying this with numerical simulations is something that I'm pursuing with Andrew McFadden and Paul Duffel at NYU. And then in addition, if we assume that all galaxies are the same, then we can say variations in the TDE are driven by variations in the black hole spin. That's certainly not, all galaxies are not the same. And furthermore, they evolve. The kind of galaxies that host 10 to the 6 solar mass black holes, like our own galaxy, are very different from the giant elliptical galaxies that will host 10 to the 9 solar mass black holes. So understanding what the stellar populations are like at those galactic centers is important for these efforts to use tidal disruption events to study black hole spin. And I'm working with Subi Ghazari to try to understand that better. I'm almost out of time. Give you a little chance for questions. But to conclude, I've been lately interested in two basically different phenomena, binary black hole mergers and tidal disruption events, to constrain black hole spin. These gravitational waves will be seen by LIGO and Virgo, hopefully in the next few years, and later down the road by ELISA. And by measuring the relative spins of these black holes using these gravitational waves, we can learn both about general relativity and astrophysics. And finally, supermassive black holes tidally disrupt stars, and those can also teach us about black holes and their spins. And that's the end of my talk. Thanks for your attention.
Thank you very much. Questions, please. Klaus.
These tidal disruption events, or these candidates which you showed from Rosa and from Galax and from Sloan, how well established are they really as tidal disruption? I mean, the Pan-STARRS one is pretty convincing, but these other ones.
I think the rates are consistent with predictions, though there are uncertainties.
But these predictions must be extremely uncertain.
Yeah, they are extremely. I would say that they're candidates. I mean, it's likely that some of them are tidal disruption events. AGN activity, of course, is also transient. Could you have something that mimics the cadence? It's when you have really, high cadence observations, like here, and you can see, boom, 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 boom. We trace the peak.
Fine.
Yeah, that's great. You're right. With something like Rosette, where you only look at it maybe a couple of times, you can fit a lot of things to a lot of different shapes to a handful of points. I would say, yeah, I wouldn't have confidence in any individual one, but there's no reason to think that the observations are limited but fully consistent with tidal disruption events.
But I guess these rates are very dependent on the nuclear star density, which is fairly unknown even for our galaxy.
I wouldn't say it's fairly unknown for our galaxy.
At these very small scales.
Yeah, it's at parsec scales. We've seen it in our own. Well, our own galaxy is a very special case that our galactic center is so much closer than other galactic centers.
Yeah, but even in that case, it's pretty unknown. I mean, for the low mass stars, which you can't really observe directly.
You can't observe the. Individual low mass stars you can't observe. We're not talking about the very smallest scales. I mean, you've probably seen pictures of these observations of these S cluster stars zooming around. Those aren't the stars that are you'd think those are the ones that are close to the black hole. Those are the ones that are the sources for your tidal disruption events. If you look at the numbers, that's not how it works out. We're talking about stars at like parsec scales as opposed to these tiny, 0.01 parsec scales. And there, we have decent estimates for the shape of these nuclear star clusters. You're right, there's a lot of uncertainties. If it was just based on rates, you could never be confident about any individual event. You need high cadence observations. Things like LSST is going to be looking at the sky every 3 days. It's not going to be like, it's going to be much more analogous to these UV observations than it is those early X-ray observations.
Would it help having a high cadence than 3 days?
Then yes, it actually, particularly for the purposes that I'm interested in, you want to catch the rise. you know, that at late times, essentially, these are orbits which are very long periods. They're essentially Newtonian orbits that are going to be insensitive to black hole spins. This late t minus 5/3 behavior is one of these smoking gun signatures that allows us to really attribute it to a tidal disruption event rather than some kind of transient AGN phenomena. But having some very high cadence observations of the earliest times would be really useful. I don't know how, there are a whole bunch of, I only mentioned the LSST because I've got a limited amount of time. There are other transient searches, obviously. The Palomar Transient Factory is a Caltech transient search. It's not going to go as deep, obviously, as LSST will. But the PTF2, which is gearing up in the next year or so, is specifically going to be looking at high cadence things. They're looking for the optical counterparts of GRBs. They're looking for a host of different things. But that high cadence will be very useful for my purposes. It won't give us the numbers of LSST, but it could give us a handful of events at high cadence.
Other questions? Laura.
Yes, I missed one thing. So can you also use this to describe, for example, the accretion from dark matter? I mean, you would suppose that at the center of the galaxy you also have components coming from dark matter.
You're asking, do supermassive black holes accrete dark matter?
Yeah, for example.
They probably do accrete dark matter. I don't know how you'd see that. I mean, dark matter can't cool. It won't make an accretion disk. It won't radiate.
Okay, well, of course it depends on the type of dark matter, I guess, but would you be able to know at least, for example, how the density of dark matter would change?
People imagine that the black hole is a very deep potential well. You could imagine that there would be a cusp of dark matter generated about this black hole. People have thought about, could you get dark matter annihilation? Annihilation goes as the density squared, so you might hope that a high density cusp would give you a bright kind of thing. People have probably looked at that, and I don't think it's expected to dominate over the annihilation signature in the much bigger volumes you have nearby. I don't know the numbers of people. It's an interesting idea. People, I think, have considered it. I don't think it's expected to be a significant source of annihilation emission.
So you talked a lot about these black hole mergers.
Mm-hmm.
And observing them in LIGO and such. Is it this observation? Are they just to see something or not to see something, or is there any devil in details to go just beyond seeing something and maybe what is how well can you see perhaps differences from GR?
Well, absolutely. I mean, it wasn't the primary subject of my talk. At this stage where we had LIGO, initial LIGO didn't see anything, people would be tremendously excited for the first event. People are thinking about the discovery. But it's not just a discovery machine. You can learn about both astrophysics and GR. I'm kind of personally interested in the connection between astrophysics and these relativity observations. But from the pure GR standpoints, so as we said, so LIGO, for example, sees in a frequency range from about 10 hertz, which is set by seismic noise that we basically there's a tiny earthquake going on all the time, and digging out a gravitational-wave signal at lower frequencies than 10 hertz is really hard. And then at to a range of about 10 to the 4 hertz, which is set by shot noise, we've got lasers going on in these cavities. We've got a finite number of photons. The photons have a Poisson noise when they bounce off your mirror, and that sets a limit at 10 to the 4 hertz. But in this window, this 3 decades from 10 hertz to 10 to the 4 hertz, there's many orbits of the in-spiral, and you can trace it to several degree accuracy over these hundreds of orbits. Small deviations to GR, deviations from Kerr metric, will lead to changes in the orbital frequency, changes in the phase that you can see. You can learn a tremendous. I kind of took that for granted. This wasn't the subject of my talk, but. For the high signal-to-noise event, I mean, obviously at very low signal-to-noise you're not going to learn a lot, but for the nearby high signal-to-noise ones, it's going to be an incomparable probe of strong-field GR. I mean, I see that as, the primary, that's my view, but I mean, I want to learn about GR, and LIGO is a great way of doing so.
I think we should use the rest of the, Michael is around until the weekend, and so we can talk to him also on Friday.
Yeah, I'll be around.
So thanks very much for your talks.